Okay, we'll wait for some couple of minutes. You can start. If you cannot talk, you can talk. No problem. The module 2 exercise question is you can say. Yeah. Yeah, you can talk.
Hello, sir.
Yeah, yeah. Talk.
Yes, sir. Regarding that module 2, I'm not able to find that one, sir. Like
Module 2, what is the issue?
exercise question. Sir, if you see in week 1, there's no lab exercises, no, sir.
Oh,
From
okay, okay.
week week 2, it starts for the lab exercises.
Ah, yeah.
So there in week 2 lab exercises, it's actually exercise 1 in the document it's given, sir.
Okay.
And in week 3, when we go in lab 2 Oslo, it straight away goes to exercise 3.1 and goes on. So exercise 2.0 and all the ray tracing exercises, those are not there.
But ray tracing is actually come in this here, na? Lab exercises in that one. They given, na?
No, sir. Like there are some more questions also there. Ma'am kept referring to some of those questions also. That exercise 2 is not there, sir. So, but now it's fine, sir. But during that time, I found it very hard to grasp the concept because uh, even those exercises could have helped me to understand it much better. And
Okay.
there's a mismatch between the lab exercises and
Yeah.
the lectures that is given.
Ah, yeah, that is so. Yeah. But that is not a big issue, na? Because your assignment question is not coming from that exercises. So always you can go from one
Yes,
one week
yes, sir,
before and yeah.
yes, sir, but that week 2, it was a bit troubles.
Okay. Okay.
Yeah.
You could install also and do other things.
Yes, that's all fine.
Okay.
So, sir, is it possible to get exercise to
I'll check
document?
whether any particular exercise two documents are there or not. I'll just check.
Okay,
Yeah.
okay, sir. Thank you. I posted that question in the
Ah,
form
yeah,
also.
yeah. I saw that one. Yeah.
Oh,
Because I didn't get
oh.
actually because it is not a what actually madam told you are saying it's like the normal imaging problems and other things you are saying.
Yes, sir. Some extra problems were there. I thought I'll be able to, like, maybe I can solve them and understand much better.
But could you do that one? So like a normal imaging of this.
Yes, sir. I had to like refer other tutorials to understand.
Okay, okay.
That's
But
all.
in my second class or something, I told now how to draw that.
Yes, sir. That one I understood, sir. Again, then some more problems were there, so I
Okay,
thought
okay,
maybe that will be good for practice.
okay.
Okay, sir. Thank you.
Okay, I think we can start. Okay, now we will today we will solve this assignment 4 and we'll see how it is going on. And before that one, anybody have the doubts regarding this? Because yeah, now our solutions are mainly or this week 4 is mainly dealing with the matrix methods and based on that one how we can solve the problems. Any anybody want any clarification regarding this matrix method or any doubt or any problem for doing this one, then you can just tell. So it's that yeah. For understanding the whole thing, you may require some basics of matrix methods and corresponding things. It is fine with all. Okay. For Apple, it is fine. What about Muhammad Sajdi?
Yes, sir. Fine, sir.
Fine. Okay. For Android also, it's fine now.
Yes, sir. There's one derivation question I had, sir. I'll ask it in the last
No, you can ask
later on.
now because no problem because
Yes, sir.
based on that one it will go on. That's it. Yeah.
So there was one general equation that was given, sir. A plus d dash and then ad plus b
Yeah. One minute.
cdd. That equation and then the one equation that which ma'am derived first.
Hmm.
How are those two related? Like, how can you relate it? I tried to equate them both. I was finding the values are not getting same. So,
You can once more you can tell what are the
so the
doubt.
general matrix form
Uh,
and the matrix form that is which is given in the assignment question.
okay. So it is a you have doubt specifically with the assignment question. You have doubt or
I tried to use the general form in the assignment question, so I didn't get the answer. I should have used the one using D.
which question you are saying? Okay, I can share
Uh,
my screen.
uh, Figure 2 answer questions from 4 to 7.
Um, Four to seven. This one.
Yes, sir.
Okay, what was the issue? This equation was the issue.
Yes, sir. If we try to apply using that general matrix method, will it work?
Okay, general matrix method means yeah, general matrix method also it will work. It will work means then there is a problem.
What problem, sir?
No, 4 to 7 means this is a, in which part of what are the issues you are having? Just
I said, like, how to approach problems like this? Should we know the main formula of it, or try deriving it from the matrix? Like, first it goes through the D1 medium, and then it hits the first surface. And
yeah,
should we do it like that, or should we straight away apply using the general matrix formula that we have? Like, there is like M H and H dash is equal to A plus C dash, and
yeah.
then the other element. Should we go like that, or should we do through the normal matrix method?
Now,
Like,
now,
this goes through the first.
now you see the first one is actually general method.
Okay. Okay, fine.
First one is general method, and they are not at all saying anything regarding the system.
Okay, sir.
Okay, they are just saying that there is a lens and there is a d1 space in before the lens, and after there is a d2 space. They are not at all telling whether this system is a thin lens system or a thick lens system or near an optical system. They are not at all telling. Since they are
Okay.
not at all telling anything, you cannot use any other methods like your h1 system. Now h1 system is derived based on, it's like a system we are equating with a thin lens formula. So that kind of system is a purely imaging system. So that is actually not a general system. The system we reduced in such a way that that will give an image. So that is not at all a general system. So we came with a lot of modification we are introduced, like b tends to 0, all the things we already introduced in that system and arrived in that H1 and H2 have a, this is a special case of this general system, you can say. So in the first question, they are not at all given anything regarding the system. Any information regarding the system is not given. Only the given is like that, it's a system containing a lens 40 millimeter focal length, and D1 and D2 are like 30 millimeter and D2 is 20 millimeter. This may not be even an imaging system, we cannot say. So the ray tracing matrix for this one will be exactly, it's a general system. So you can see that A, B, C, D, all values is a positive quantity or the a particular quantity is having. Okay.
Yes, sir. Yeah.
We cannot say that this will give a proper imaging. If it's a give a proper imaging, what is the condition? Your B will automatically become 0. Since this a B is not at all 0, this is not an imaging system. So you cannot equate that.
Sure. But this equation, we have to assume B equal to 0, no, sir?
No, no, no. Yeah.
Because D1 and then D2, and then there's a constant beta. So
Where?
in that equation, B is 0, sir.
Where?
The ray tracing matrix is given by. If we try to apply it with the general formula, I think we'll get B as 0.
Means I didn't get it.
So
Which is general formula?
there's another one, no, sir. Afterwards, ma'am derived another one.
Yeah. That is
A
saying that.
A plus CD plus like
Ah,
that.
that is not a general formula.
Okay, okay, fine, fine, fine.
That's an imaging system.
Okay, fine.
That's
My bad, my
imaging
bad.
system. Yeah.
Okay, got it, sir.
This is this formula. This whatever you are seeing on the screen is a general formula.
Okay,
So,
sir.
in order to become the general formula to an imaging system, we have to modify. We have to put a constraint such that your D1 should be like an object plane and D2 should be like an image plane kind of thing. It should come from there. In order to come from there, we should get a condition like that way 1 by D1 plus 1 by D2 should be P by N. So, that if you apply that constraint there, then we can actually apply all the imaging condition. From there, actually, you can solve with respect to your values of the matrix of that lens or the system. You can get it to planes corresponding to a principal planes corresponding to a imaging system. So you are actually making a system to an imaging system which is behaving like a thin lens. So after you made that system, then you can apply the thin lens formula. But it's not an exact thin lens formula. The thin lens formula with on the principal plane. So then your life is become easy. You don't have to worry about the lens curvature and all other things. You can just define the lens with its principal planes. So that's actually it will make your life easy. So by before making itself, you already told that that is an imaging system. That's why you can do all the things. This is actually whatever you are seeing in the first question is not at all an imaging system. If it's an imaging system, you can see that the matrix automatically it will come, your B will be 0. But here it is B is not at all going to be 0. So I can directly seeing this matrix, I can say that just a C, A, B, C, D, all the option B is not at all 0. So I can directly see that this is not a proper imaging system. I can directly see by looking the matrix. If it's something like it's
Okay,
a
sir.
0 came, then I can say that it's a imaging system. I can directly say like that. So this is actually
Okay.
general form. Okay. So whether all people could do these assignments, anybody having some doubts regarding even installation of Oslo, you people can tell. We can start then even. Okay. Okay, somebody say ask her that. Okay, when I am presenting my screen, I cannot see that comments and other things, so you can directly ask. I don't have any issue with that. Okay, some books. Actually, this is actually some more exhaustive. I'm feeling means that you can just for this question. I don't think that even you can refer what are the books which Madam referred. But for this particular course, actually, the lectures will be more than enough. I'm feeling like that. And you can just play with your Oslo software also. It's not, you people are thinking, more feeling it a very little bit difficulty or something. I can ask.
Hello, sir.
Yeah.
Sir, in the first three questions from Oslo, we are facing some difficulty
Okay. Anyway, I'm
to
going to
solve the
solve that.
questions.
Yeah.
Yes,
You,
sir. Please
okay.
solve, sir.
Okay. You people installed Oslo, na?
Yes, sir.
Okay. Could you do this imaging of this normal lens and other things?
Yes, sir. Yes, sir.
Okay. So here you people are facing some difficulties. Okay.
Yes, sir.
Okay. Let's start from our first question itself. All are in PC or mobile or something, such that if you want to, you can also do parallel.
Yes, sir.
All people are in PC or in mobile.
Sir, I am in PC.
Okay. So you can also do that one parallelly, and you can see parallelly if any difficulties there, you can go.
Okay, sir.
Okay. So I am opening a new lens. Hopefully all new, all people are installed Oslo. So now actually, yeah, one problem with our thing is that I am not seeing the screen. So if some doubt is there, you can just tell, because without hearing, I cannot say that you people are here. I am taking new lens. No, I want some three surfaces. I'm giving some three surfaces. Anytime if you have a doubt, just ask. Okay. Now this is,
Okay, sir.
so this is the lens. I am going to create a lens according to our assignment question. Now see what kind of lens I want. Already a beam radius of 5 mm and a field angle of 30 degree. I want to design a spherical glass ball of radius 20 millimeter, and the refractive index of the first hemisphere is 1.5 and that of second hemisphere is 1.6. First, let us see how they want. You people are seeing now?
Yes, sir.
Yeah. They want a sphere, but the sphere is not a full sphere. It is a two hemisphere composed of refractive index 1.5 and 1.6, and this radius of the sphere is 20 millimeter. Okay. Now in the Oslo, we can start. Now in Oslo is saying something like that way. Just to go through. Oslo is saying that okay, some rays coming from here. Okay, so that beam radius and beam angle we will give. So that I am giving here. Okay, beam radius they sold 5 mm. So 5 mm I am giving. Beam angle, field angle I am giving 30 degree. Okay. Now it's like a object distance. So I am not going to put that object distance here. So let it be the one. So now I am going to reach my first surface. This is my first surface. So they have given that radius of curvature is 40 mm. I think this thing. Ball of radius is 20 millimeter. So radius of curvature is 20 millimeter. So I am giving radius is 20 millimeter. And thickness. Now we will see how much is my thickness of my first. There is radius is 20 millimeter. So this radius of curvature is 20 millimeter. So what should be my thickness of my first surface? This will be the thickness of my first surface. So it should be how much? This radius of curvature is
30 mm, sir.
how much?
30 mm.
Why 30 mm? This is radius of curvature itself is 20 mm. So it's a hemisphere part. So
Okay, okay. 10.
It should be 20 mm.
Yes, sir.
Okay. So I reached at that hemisphere area. So the thickness is 20. Now see aperture radius. Now just to see that what is how my thing will look like, because I didn't put anything here. Now I want an aperture radius. Now aperture radius is the portion in which how much light is coming. So I can say that this is my aperture radius. I should get a minimum aperture radius of this much. Correct? So this is the full aperture. Okay, this area means if you considering it a cylinder kind of thing, this is the full aperture. So the radius of the aperture will be how much? The same as the radius of the sphere, na? So that
Yes.
will also be 20. So we'll give 20. Then comes, this is the my first surface. So it is not air. It should not be air. It should be a particular glass of refractive index. So you are going to give a value. So you can directly give a value to direct. So it will just give x a glass number. So there are three different wavelengths are used. Mainly we'll use the first wavelength. So I am saying that the refractive index for all the wavelength is 1.5. Okay. Okay. Now we took a particular glass here, glass one. Okay. You see, you got the first surface. This is my first surface. Only first surface is this portion only. This is actually going to be a second surface. Now, now we reached here. Actually, now we reached at this interface. Now my second surface is this one. This middle portion will be my second surface. So what will be the radius of curvature of the second surface? It's like a plane. So I have to put a second surface of what will be the radius of curvature for Oslo. Radius of curvature is actually infinity, but in the Oslo we cannot put infinity. We have to put if there is a plane, the radius of curvature should be 0. Any doubt for that one? Now we are moving from that medium. Now we want the remaining portion. Now we want this remaining portion. What will be the thickness of that portion? That will be again 20. Na? It will be again 20. Such that the full sphere area is covered. So I'll give D. But you can see that now only aperture is selected this much. That's why it is coming like 11.031. But actually I want a full hemispherical area. So I will put that also 20. Now you can see that that dotted portion is now extended till this much. So this much aperture that we selected. Now actually it is given some big refractive index thing the other side. And second portion is it's not at all air. It's a different glass having refractive index 1.6. So put a direct the give refractive index like 1.6. Here also you can put it. Actually there is no need to put everything, but yeah. So I'm just saying that all the wavelengths have the same refractive index. I'm just saying that it will not be exactly like this. So I'm putting. Now you see, it will come like this. But this is the second surface. This is second for surface. It is extending. Now the third surface should be my the other side of my sphere. So radius of curvature is same, but it should be in the opposite direction. So I'll give minus 20. Okay, and thickness you don't need to give much also. Here you see, here it is not coming till because it's not take everything here. So here thickness is actually doesn't matter. Here you don't need to put thickness also, but I'm just putting some extra thickness there, such that you will get some more ray afterwards. But here you take that aperture as a full, such that now you got the curve. Origin image you got now. Any doubt for this one?
No, sir.
Now it's clear.
Yes, sir.
Now, now what? So you made the things as per the requirement. Okay. Now you want to see how we can easily take this value from here. Now what is the question? Question is, for a beam of this thing you already made. If you want to put like a just screen kind of thing, what you put, you will give a solve here. So you will put a solve, accelerate, save, and you will draw surface control general. You will draw. So you can see this is the portion where actually it is a focuses. This focuses a image from an object at a distance from, you see, 1 into 10 raised to 20. It is like an infinite. If an object is placed at an infinity, it is giving an image at, you can see exactly 9.941502 centimeter from this surface. Okay, this is the inference which we can get from this system. Now we want easily find out the parameter of this system. Okay, principal points are located here. I will find out. Okay, now see here actually we have the data of this. Go to the setup, you can see different data here. Okay, object distance, it's like a infinity. Okay, object to pp1 distance. If the object is at infinity, then infinity to some distance will be automatically, it will be infinity only. So that also same. Then image distance, this Gauss image distance is actually giving the image distance from the surface of the lens to the particular image. Then it is like a pp2 to image. pp2 is actually your principal plane 2. So if I want to know some distance, you can easily put like this way. What you want to do? Give some. This is like infinity match object distance. Just give some arbitrary value. Let it be 100. Now you see, I put object distance at a 100. Object to principal plane 1 is a 121.754386. Okay, you are seeing this one? Hello?
Yes, sir.
Yeah. What does that mean? So I put a, this is my, this name is, so I have a system. I don't know the properties of the system, but I know one thing. Like when I kept my object at a 100 centimeter from the first surface, it will have some principal plane now. And I am saying that this is my principal plane. This is principal plane 1, and I am saying this is my principal plane 2. I know that one, when I place one object here, I am getting some image somewhere here. And the distance, this is I defined 100 centimeter. I put my image object. Then I am getting an image at a 9 point some centimeter. Let us see. 18.3520. 18.35. This is a 18.35. I am getting. And they already given what is the distance. What is the thing? Object to PP1. That's a 121.754. 121.754. So if there is an object plane, a principal plane, that is like a this much distance. This is a 121.75. And there is an image plane to image, PP2 to image, and that distance is given as a 36.480, 481. Now you see, can you find out the answer of the question from this data?
Yes, sir.
Yeah. Now tell what is what will be the right answer. Principal point is locations are, let's see, 21.875. So we are getting 21.75. Okay. From surface 1. So we are getting here this distance as a 21.75. And minus 18.128 from surface 3. So 36.48 minus 18.35 will be, and this is the other side, so it's like a minus 18.13. So what will be the answer? 21.87 millimeter from surface 1 as well as minus 18.128 from surface 3. So this thing and this thing will be correct answer. Okay, got it?
Excuse me, sir.
Yes.
Sir, here the object distance is 100 we take 100 centimeter, right?
Yes.
Sir, if we take any different value like 200 or 300, then the value I think same or change.
Just
What will
tell before changing that. Just tell that whether it will change or same or change. I'm going to change it, but before I'm changing, just give a guess whether it will change or not.
sir, I think it will not change, sir. Object to PP1.
Yeah. Now I'm just going to change like 200. Okay.
Yes, sir.
What happened to that one?
It is also increasing.
Yeah, increasing in what range? That is that.
200.
Yeah, it is just increase that. It's like objective PP1 only. 221.7543. The same value, it is just increased. So
Yeah.
actually, what we are doing, only to understand for us, we took that distance. Actually, now see, you can see this drawing now. This is
Yes,
actually
sir.
this sphere. We just made an equivalent of that system. Instead of taking this big sphere, we just took these two planes only. So I can represent the whole big spherical drop only by selecting these two planes. So now actually this red sphere as well as this green or that blue two planes are actually equivalent. So this is actually the property of this sphere. It is not the property, it is not at all depending upon our object which is kept in front or the object distance. This is actually the property of the sphere. We can make the sphere equivalent to two planes where the planes will behave as an imaging system equivalent to that sphere. So if you change that distance, your object distance also, this principal plane distance is not at all going to change. The principal distance is actually the property of that particular imaging system. So based on that property of that imaging system, we are defining the principal planes. So that's why actually you can see that. You may, I don't know. Oh, yeah, somebody asked me that question. Na? We are solving that principal planes. Like you are getting that matrix C is equal to minus P by N. Like that way we are defining something like P is equal to minus N prime C. D is equal to N by N prime minus D by C. D prime is equal to 1 minus A by C. Okay. Any doubt? Means they are asking that question. So you people know that corresponding to this one. Now you see that this is composed of how many surfaces? This is a one surface, one curved surface. Correct?
Yes, sir.
Yeah. So one curved surface, I am putting it as like a matrix M1. Then there is a air gap, not air gap. There is a glass path. Corresponding that one, I am putting to a matrix M2. Then there is a change in diffractive index from here to here. Okay, corresponding there will be one matrix M3. Then again one another glass gap. Corresponding there will be refracting index M4. Then there is a refraction from here to here. Corresponding there will be a matrix M5. So you can get a matrix like M1, M2, M3, M4, M5. And if you calculate, if you know the properties of this, the properties which is given by Oslo, we have given the refractive index and radius of curvature, thickness, and again there's a parallel surface, then again a thickness, then again the refractive index change. Like that way, corresponding we will get a M matrix for this bubble, or not bubble, this sphere, and that matrix will have corresponding A, B, C, D. So if we calculate, this will be some particular value for this one, because we know all the parameter for this one. So it will have a particular value for this A, B, C, D. And with that parameter, with the A, B, C, D and parameter, I can define two distances, three parameters like P, power, as minus n prime c, where c is actually the value of this matrix. Similarly, d1 is equal to 1 minus a by c, d2 is equal to n by, sorry, it's a d prime, d prime as 1 minus a by c, d as n by n prime minus d by c. See, now all these values have some values now. N prime, if I are considering the outside of this system, n prime will be 1. So it will give a p is equal to minus c, it will give. And that c is actually the matrix of this particular bubble, which is coming after you solving with all the matrix, combining this m1, m2, m3, m4, m5. Similar way, you will get a d1. d1 is given by the principal plane 1. d2, oh, sorry, this is d, yeah, this is given by pp1. d prime will be given by this d2. Everywhere it is using that matrix value only, 1 minus a by c. So if you already defined that particular matrix for this sphere, then you can directly derive this equation. Actually Oslo is deriving that equation only. So then the corresponding to this particular sphere, you will get a value for your d and d prime, which is nothing but it's a principal planes. Then if you got the principal plane, you don't need to worry about this sphere, so curvature and other thing. You can just solve all the equation with the help of these planes. This is the way it is going. Okay. Now see. The distance between principal point 2 and the focal point is, the distance between principal point 2 and the focal point is, what is the principal point 2 distance? Here also with Oslo we can do two times, two ways. Now can you use this image distance as focal length? This, there's some 14.009662. Can we use this distance for using this focal distance? Yes or no? Anybody? There is here is written Gauss image distance.
So sir. If the rays are parallel, then yes, no, sir.
Yeah, but whether rays are parallel or not.
For the
Now I given a object distance of 200 millimeter. So object is at a finite distance. So I cannot say that all the rays are going to be parallel. If how all the rays are will be parallel, if my object is should be at a infinity, then only all the rays which is coming from that point will be parallel. Okay. So this is a finite distant object. So I cannot just say that image distance is my focal length. So I cannot say like that way. So this image distance I cannot take. But I already got the parameter. What is this one? Focal length is here given. Or here itself I am having my effective focal length. Correct? What is my effective focal length? 28.07015. Correct? Any doubt? This is focal length. What is meant by that? Now I am saying that my sphere I have two principal plane. Okay, and I have a focusing area. Now the question is the distance between principal point 2 and the focal point. What is the distance is called? Now the parallel rays which is coming like this way are focusing at this spot. Okay, no doubt. Focus like this. And actually inside it will be something different. So I just put. I don't know how it is going to travel, but it will travel in such a way that it will focus. But what is this distance is called? Principal plane 2 to my focus spot. Focal plane. This distance has a particular name. What is that? Niggas. In normal lens, if parallel rays are coming, means at thin lens parallel rays are coming and it is going to focus at a point. The distance between length and the focus is called, what is this distance is called? In the case of a normal lens, what is this distance is called? Tell somebody. This is easier. Nah. People are hearing. Nah? I'm not seeing my window.
is it focal length?
Yeah, this is called
Focal length. Yes.
focal
From the
length.
object. Principal plane.
This is the normal focal length. Now, this is a thin lens, so there is no thickness. But in the thick lens, actually, we are defining the focal plane or the focal distance with respect to our principal point 2, and that distance is called. Now you may have got some clue. This is focal length, and this is what?
Back focal length.
Yeah, it is not back focal length. Back focal length is actually will measure from the back side of that. Your this one. This is your back focal length. This is what?
Image distance? No, no, no.
It's not image distance. Now you got from clue from here. This is focal length. Okay, you are measuring from the back side of your lens, then it's a back focal length. Then this is actually you are replacing this whole sphere, and you are just actually making a two planes. So now onwards you don't worry about this all things. You are actually changing or replacing this whole thing with these two planes. Actually, it is giving an effect of the sphere. These planes are giving an effect of the sphere. So we can call this focal length as this is your effective focal length, EFL. So that what already calculated who? Roslow already calculated this one. Whatever you are giving is a 28.07. This is actually the effective focal length. 28.07. So that is the question. Instead of asking what is the effective focal length of the system, they are just asked what is the distance between your principal point 2 and the focal plane. That is actually called what? That distance is called effective focal length. So see. So this is 28.07. So they are giving mark for 28.03 to 28.09. Got it? Any doubt for that one? Any doubt? If you have doubt, directly ask. If you didn't understand anything, ask. If you understand something, also ask. Whatever the doubt you ask. Okay? Hope that is clear. If you didn't clear, just tell me. Now, if the refractive index of the entire sphere was 1.5, the effective focal length will be how much? So, what I have to do? Tell. What I have to do in this system? What I have to do? Now, I have three systems. One is this surface, and which have a refractive index of 1.5 here, and there is another hemisphere which have a refractive index of 1.6. Now the question is that I don't want these two surfaces. It's like a whole big sphere, so all the refractive index is equal to 1.5, I think. 1.5. So what I'll do, I'll just change that 1.6 glass to 1.5. This is my glass. So direct, so it was 1.6. I change to 1.5, change to 1.5. Right. Accept. What is the focal length now? What is the focal length? People are seeing now. I'm not. People are seeing that. What is the focal length now? New focal length. It was some 28.07 before. Now, what is the focal length? People are hearing that. I cannot see. Oh. Yeah, sorry, I got disconnected.
Sir, actually, in that question,
Yeah.
sir, we are unable to change the refractive index. Sir, we just assume that from the wavelength glass and 1.00, I
uh,
think it will not, it didn't change.
okay, okay,
So from the refractive index, that's why we are not
okay. So you
getting
just change it.
correct answer. Yes, sir.
You didn't change it. Okay, so everything came as glass then. So nothing came out as you couldn't even make this kind of sphere also.
Yes, sir. Yes, sir.
Okay, okay. Yeah, actually, when you're putting this direct thing, actually you can change the. Okay.
Yes, sir. Actually, first time where BK7 and BK type of things means material is
Yes.
coming, and if we change glass 2, then only uh, I think index there is an index. I think 1.00 it is means exact value. It will not change means.
Okay, okay,
So we are unable to change. Then refractor is different, and we are not getting 1.6 also, sir.
okay, okay,
That's
okay. So that for all three question is also difficult then.
yes, sir. Three questions we
Okay.
got.
Okay, so instead of yeah, they put some VK7 and VK5 or something, you could have
Yeah,
directly
yeah,
got
yes,
that
sir.
one. Okay, yeah,
Yes, we are, sir. We are not means find the how to get the refractiveness 1.5.
okay, okay, yeah. It's like a, yeah, it's like easier. You could have directly. Okay, that's what. Yeah, we didn't. Yeah, before that one also people are directly taking some particular glass other than defining that refractive index.
Yes,
Yeah.
sir. Yes, sir.
Okay. So okay, now that three questions are acceptable, means solvable, na. So now you go for this 47. So this thing actually okay. So people are saying that
Actually, in third question, it is saying that if refractiveness is changed 1.5, then effective focal length.
yeah, you are seeing my window.
Yes, sir.
Okay, when I was changing, you people are means did you see that one? I don't know
Yes,
that.
sir.
Uh,
Yes, sir. Yes, sir.
because suddenly I got disconnected and I came to know after some time.
Yes, sir.
Okay, now the effective focal length will be
Third. No, this is focal length.
yeah. Whatever it's a focal length it is showing in this auto draw is actually effective focal length.
Okay, okay, sir.
Like here also you can see that
Yes, sir. Yes, sir.
EFL is equal to 30 and here also focal length is equal to 30. Okay,
Okay, sir. Okay.
now going to that 4 to 7. Or here actually they given a lens system containing three distance, two distances and a lens. So they given a f is equal to 40 millimeter. There comprises of a lens of having a focal length of 40 millimeter, and there are two distances. One is in front of the lens, there's a D1, and there is a behind the lens, there's a D2. And actually, they are asking for a ray tracing matrix. So you people already know this one, na?
Yes, sir.
Okay. How? What is the ray tracing matrix for a free space?
Sir, the last equation is matrix is 1 minus d by 2 upon f,
Okay. So
then
yeah,
d1 minus d1 and
yeah.
so on.
Yeah, if you want yeah, if you want to do like that way, means if you are remembering that equation, then it's okay. So otherwise what you have to do, you have to, but you people has to remember all the ray tracing matrix equations for different surfaces or the medium.
Yes, sir.
If this is given also, if that is not given also, you should have derived that one. So I'm just mentioning ray tracing matrices of this one. So there are three or four ray tracing matrices you have to understand. They are one like a free space, like a free space. So it is ray tracing matrices for free space. moving at a distance d. It will be like theta 1, theta 2, phi 1, phi 2. The corresponding ray traces matrix will be 1 d 0 1. Similar way, if you see that there's a refraction at a plane surface, then the corresponding ray traces matrix will be 1 0 0 n1 by n2. Well, this is n1, this is n2, and if there is a curved surface, n1, n2, and it's happening like this way. The corresponding ray traces matrices will be 1 0 minus n2 minus n1 by n2 into r n1 by n2. And if there is a thin lens, the corresponding ray traces matrix will be 1 0 minus 1 by f 1. So this thing anyway you have to remember this all these four things. This thing also you can derive, but it is better to be remember this all four things. And if you could solve these things, then you can directly get this equation. So if it's a put an arbitrary distance like d1, like d1 and d2 with that lens, you will get a, if you are solving as it is, then you are going to get a this one. This one will ray tracing matrix can be given like 1 minus d2 by f, where d2 is that distance. Then d1 plus d2 minus d1 d2 by f minus 1 by f 1 minus d1 by f. That is given as your ray tracing matrices for that particular system. A lens separated by two distances d1 and d2. You will get like that. Okay. Now you already know this is the situation. 1 minus d2 by f, d1 plus d2 minus d1 d2 by f, 1 minus 1 by f, and 1 minus d1 by f. These are the four elements, and this is equivalent to, for ABCD matrix, you can say that A, B, C, and D. Okay. Now see, when does this D matrix become 0? When the D matrix becomes 0, corresponding to D, what is the value? This is the value. Okay. So if you want to the D matrix to become 0, it should be like a 1 minus d1 by f is equal to 0. Implies 1 is equal to d1 by f, d1 is equal to f. Okay. So that will be the answer.
Option
d1 is
A.
equal to f. Now the question. Now the question comes. Which of the figure represents the case for question 5? Tell. Somebody can tell. Which of the case saying figure for question 5 means D is equal to 0. What is meant by D is equal to 0? Now see what is actually given by the ray tracing matrix. How you will define a ray tracing matrix? So there is a optical system which you don't know. This is some black box, but it's an optical system that only you know. What are the things you know? There will be some optical axis will be there, and one ray will enter. Okay, and outside also somewhere some ray will enter. This is the thing which is no. This is actually the optical system. While entering, it will have a particular height y1, and it will have a particular angle of incidence theta 1. While exiting also, it will have a particular height y2, and it will have a particular angle of emergence theta 2. So a transfer matrix or a retracing matrix will define this particular system in terms of 4-letter ABCD, which is given like y2 and theta 2 is equal to A, B, C, D, and y1 theta 1. If you define y1 and theta 1, then it will give y2 and theta 2. So actually, if you know that where it is where the ray is going to hit and at what angle it is giving, you can directly get the value as how it is emerging, at what height it is emerging, at what angle it is emerging. That's actually the method of this ray tracing matrix. Now they are saying that D is equal to 0. You people all know this matrix multiplication, na? How it is matrix getting multiplied?
Yes, sir.
How it will get multiplied?
Sir, AY1
Yeah.
B
So I
B
can say
theta 1.
that y2 is equal to a y1 plus b theta 1.
B theta 1.
A y1 plus b theta 1. And theta 2 is equal to c y1 plus b theta 1. Now you see that a and b are actually values which defines the height of the emerging ray. C and D are the values which defines the angle of the emerging ray. Now see, A is giving the value of height with respect to the height of the incident ray. B is giving the height of the emergence ray with respect to that angle of incidence. Similarly, theta C is giving the angle of emergent ray with respect to the height of the incident ray, and D is giving the value of angle of emergence of the ray with respect to the angle of incidence of the incidence ray. So now they are saying that D is equal to 0. If D is equal to 0, whatever the angle a ray reaching the lens, it is saying that if the height is a particular thing, then the value will be the angle of emergence will be same. They are saying something like that. Got it? If d is equal to 0, whatever the angle of incident ray, the angle of emergence will be always same if that's a particular height. Got it? Any doubt?
No, sir.
Okay. So how you can define that system? Now I can say that I have a system here, and I am saying that I am taking a particular point. And I am saying that theta 2 is only depends on height. So and so I can say that I'm saying that this is that particular theta 2, and I'm saying that whatever the angle, because d is equal to 0, whatever the angle is coming, there is no effect of the angle. So if that height y1 is constant, if my y1 is constant, whatever the angle the ray coming to the y1, it will emerge out as a particular parallel angles. Correct? This is the thing which is giving d is equal to 0. True? Correct? Huh? Any doubt?
No, sir.
Yeah. Now just refine that question or this system. Just we can say that this will be equivalent as a lens having a system in which whatever the angle coming from a particular thing, it will emerge out as a some parallel thing. Correct? Can I say it like this way?
Yes.
If I am defining my d is here, d1, d2 here. Okay? So see, which will be that question answer.
Option D, I think.
Let's see, the answer is D. Okay?
Yes, sir.
Now see, which of the ray tracing matrix element is 0 for all rays in the case of shown in figure? Am I audible?
Yes, sir.
Right. Now we see, this is the question. Which of the ray tracing matrix element is 0 for all the rays in this case shown in figure? This one is a question. Okay. What is this condition is called? What is this condition is called? You see, madam already taught in the class. There is a lens or some system. I will not say it's a lens. It's a lens system or something. And I have a plane. Here also I have a plane, and some rays are coming from particular point with the lens. It is reaching out. Okay, it is coming from at a particular point and it is reaching at a particular point. Correct? So I have my y2, theta 2, a b c d, y1, theta 1. Okay. Now see all the rays coming from a particular point is reaching at a particular point. These are like different angles now. This is at a particular angle, this is another angle, this is another angle, this is another angle, this is another angle. But irrespective of the angle, whatever the lines which is coming from a particular height is focusing at another particular height. So it is something which is connecting height to height. So y2 is equal to a y1 plus b theta 1. Now you see that whatever the angle may be, it is not at all depending on that one. So if it is a particular y1, it is connecting a particular y2. So y1 is connecting to y2. As long as the y1 is constant, y2 will be also constant. So there is no angular dependence here. So this quantity should be
0.
0. So what is called, this condition is called all the particular point, all rays from a particular point is reaching at a particular point after passing through an optical system. It's called imaging. So it's actually an imaging system. That's why we are called always B is equal to C for 0 for a imaging system. Okay. Now we can go for another question. For reflection from a planar mirror, the ray tracing matrix is. Okay, already showed the question answer. This thing actually, I think madam told in the class also, na?
Yes, sir.
Any doubt for that one? Whether I have to explain
No, sir.
reflection? So it will be like what is the difference? This just change the
Angle.
direction. It will not change the angle actually. That's the thing.
Angle and the height also same, na, sir?
Yeah. Now just to see that it is a reflection from the planar surface. Just to see, this is angle of incidence. Now the ray is coming here, and this is like a normal, and the ray is reflecting. Now if I am drawing a ray, it will be like my theta 1. Okay. Now this is the direction of incidence. Okay, rays coming like this way. So this is theta 1. That will be same as this theta 1. We know the law of reflection. So this will be theta 2. So this is the direction of that reflected ray. Now the direction of this optic axis also the other side. So there is not at all any sign convention also. Okay, because even the whole optic axis itself is rotated to the other direction. So here also along the optic axis there is a upside angle theta 1. After incident is here, the optic axis is in this direction, and there also the same direction theta 2. And already we know the laws of reflection, theta 2 is equal to theta 1. Okay, so and what about the height? What is coming here? The height is y1. When it is emerging, it is just emerging. Don't consider any distance at this one. This is after passing this much distance. But just after the emerging, it will be the same distance theta 2. Sorry, y2. So y2 is equal to y1, theta 2 equal to theta 1. So if you want a matrix, y2 theta 2, y2 theta 2, y1 theta 1. If you want theta 2 should be theta 1, this should be 1, sorry, 0, 1. And if you want to, y2 should be y1, should be 1, 0. So you will get a transfer matrix as 1, 0, 0, 1. Okay, 1, 0, 0, 1. Now the question. Yeah. In figure 8, E and V prime are surface point of the lens. P and P prime are principal points. R is equal to 40 mm and R prime is equal to minus 60 mm, and radius of curvature total thickness T is equal to 20 mm, NR is equal to 1, and refractive index of lens is equal to 1.5. Answer the question 9 to 10. How you people did this question? Can you get your feedback?
Sir, actually we did from Oslo.
Okay, yeah. That will be much more simpler way.
Yes, sir.
Otherwise, how will do?
Otherwise,
Otherwise, how your people are going to do? It is going to be a cumbersome process.
yes, sir.
Yeah. How you can do that one?
Sir, actually I didn't try.
Okay. Now you have an idea. Now you can say that this is a thick lens.
Yes, sir.
This is a thick lens. They are asking for EFL of the system, effective focal length of the system. They are asking, and they are asking V prime and P prime. What's the distance? So I have to put but how? Okay, I'll ask one question. How you could put this 1.5 refractive index there?
Sir, actually I think BK 8 or 10 is something 1.52 or 1.51.
Okay, okay, okay.
So
Yeah.
from there we got the idea about the answer.
Okay, okay. Yeah, good. Yeah,
But the
that's it.
second 10 question we did wrong. Question number and I don't know why.
Okay,
Uh,
let's try. Okay. So if you are not doing Oslo, how you will do? First what you have to find out. Now you can see that how many surfaces are there. Surfaces in the sense, see how many transfer will be here. Here there's a one transfer. Say curvature transfer. So corresponding you will get a matrix M1. So that we already said na, the radius of curvature transfer means there will be like a one matrix corresponding to what kind of, yeah, transfer matrix for a curvature refraction. So you have to put a 1 0 minus n2 by n1. The n2 should be 1.5 and n2 minus n1 by n2. Okay, yeah. So put that 1.5 here and n1 is equal to 1 here, n2 is equal to 1.5, and the radius of curvature will give that one, and you will get a particular transfer matrix for that value. Then so you will get a particular value for this m1. Then there is actually a transfer in a particular medium having a thickness at 20 millimeter. So you will get a second matrix here, m2. Then there is a third matrix, m3. Okay, then you have to cascade these three matrices, and you will get a the main matrix m for this matrices are, first it will travel through m1, then m2, then m3. So you have to find out m3, m2, m1. Then you will get a matrix of m. Okay, then this m will be having a, b, c, d. It will have some four number, some number, some number, some number, some number. Now here you have to define, you think that there will be two principal planes P1 and P2, which is having at a distance of d and d prime. Then and you have to see there will be a power element P also. So these three variables you have to find out. So you can find out this three variable as we have that equations corresponding to that.
P is equals to minus n prime into capital C
P is equal to
minus n
minus n
prime.
prime C. Yeah.
Yes, sir.
So you will get P is equal to minus n prime C. Here n prime will be 1 because again the third means that the refractive index is air. So
P is equals to minus.
and P is equal to minus C, you will get it. Then D is equal to what is,
N by n prime minus capital D upon capital C.
yeah, n by n prime minus D by C, and D prime is equal to 1 minus A
2 by C.
by C. So by finding out all the values, you will get this P, D, D prime. So that you will get D is actually your first principal plane, P1 or P, yeah. Then D prime is equal to your second principal plane position, P2. And from the actually you can, and P is actually the power of your lens. So from these three values, you can find all the values. But the easier method is like that way. We can directly give that parameter to Oslo and C. Let us see. This thing I didn't put it there. So what are the parameter they given? R is equal to 40 millimeter, R prime is equal to minus 60 millimeter, radius of curvature. Okay. 40 and 60, and thickness is 20 millimeter, refractive index is equal to 1.5. Let us see what Oslo is doing. So I am putting a new lens. R is equal to 40. 40 and minus 60, thickness 20.
Sir, from that equation,
Uh,
P is equals to minus n prime C. So n is equals to 1. So what is the value of C, sir? Capital C?
that C you have to find out from this value. That's why it is becoming cumbersome. Na?
Okay.
That C you have to get by putting the value of all the surfaces. So you have,
Okay, from the matrix, right, sir?
yeah, from the matrix you have the values like there are three matrices will be there,
Yes, sir.
corresponding to the first curvature, then corresponding to the thickness through which that light to travel, then corresponds to the second curvature. So there will be
Mhm.
three curvature, and all the parameter for the curvature you know. First curvature has the parameter radius is equal to 40 millimeter. That is the
Yes,
one
sir.
which they are given.
Yes, sir.
So from there, and there are two refractive indices. One is
Mm.
left side is air, right side is glass. So that N1 and N2 you know. So you have to put that value in that first matrix.
Yeah, yes, sir.
Then second matrix is a transfer matrix for the direct transfer. 1, D, 0, 1. So that D should be thickness. That
Thickness.
also given. Then third one is actually the another one.
Another one means
So,
curvature.
so with this giving this parameter, you will get the three matrices. Then multiply the
Okay.
three matrices,
Okay, okay.
and the product of the matrix will give your A, B, C, D matrices. So there A, B, C, D will have a particular value, and put
Okay, okay.
that value to your this equation.
Hmm.
By solving this equation, you will get these three values. That's
Yes.
why it is becoming cumbersome.
Okay. Got it, sir.
Yeah.
Thank you, sir.
This is the thing actually Oslo is doing. When you are giving these parameters, just calculating and giving the values.
Yes, sir.
Okay.
Sir, this PPT, this slides are also shared in the NPTEL
Okay.
Means link.
Okay. Till now I didn't share it, but yeah, I will share this one together. I just want to do some edit, then I will directly share that all the
Okay,
slide
okay.
as well as the video. I will share this one.
Okay, sir.
So let's see. So, so 40 and minus 60 thickness is 20 mm. For thickness is 20. So minus 60. Okay. Plus 21. The so this is 20. So I don't want this surface. So you know why it is showing that this kind of big thing?
Yes, sir.
Because we didn't given any image parameter and other things. If you increase that thickness, you can see that it is giving, because that aperture stop is 1 mm. So if you want to see something kind of the lens. Okay, this is the thick lens you want. Now what's the question they are asking? I said that the EFL of the system. Yeah, that we got 51.42857. If you design this in the Oslo, but yeah, from here directly we'll get the answer. But yeah, that is the original process. If you want to solve that one, if it is if they are not allowing the Oslo, this will be like a essay type question. Okay.
Yes, sir.
Yeah. Yeah. Here you directly got it 1.43. Now see the distance between P prime and P prime means V prime and P prime. So V prime and P prime means V prime is actually the one of the surface. Okay. So I want that exact position of my P prime. Okay. So what I am going to do, so I am going to put at a distance at a particular. It's a easier method I am going. Okay. So I'm going for this setup. This is like very high distance. I'm going to put some 100. Accepted. Now see. Now see image distance. Image distance is 91.578947. Okay. What is mean by this image distance?
Which, sir?
Here is some gauss image distance.
Yes, sir.
91.57. That is actually the
L.
distance from, if you have a particular system, just consider this a particular system. It can be thick lens or thin lens or anything that, and it has a, I'm saying that I have an object at a particular distance. Sorry, an object at a particular distance, and there will be some image at a particular distance. And this your Gauss image distance is the distance from your back side of your lens to the image. Okay, this image they are giving it as 91.57 because I put out my object at 100. Okay, so 91.58 and just 91.58, and they are saying that for this particular imaging your pp2, there is a, from the Oslo we are getting that pp2 to image is 100.15. Okay, so there is some pp2 here, that's there is some principal point to here such that this image to this image is a 100.15. 100.15. 100.15. So what is this distance will be? 100.15, 91.58. How much? Correct na?
8.5, yes, sir.
Yeah. Now you see.
Sir, can we say that the distance from principal point
Hmm.
to the means where the image is formed focal point, can we say that this is the effective focal length?
No, that will be effective focal length if and only if your object is at infinity.
Okay.
So that you can see here. Now you can see that. Now this is you got here na. Now you see that. Now I am going to increase that length. I'm going to put my object is something like infinity. 1 e raised to 20. Now it's going like a parallel.
Yes, sir.
Okay. Now you see that 42.8571. This image distance.
Mm-hmm. Yes, sir.
Now you see PP2 to image.
51.42. Yes,
Yeah,
sir. Effective
that
focal.
yeah, that is some more near to your effective focal length.
Okay, sir.
Till there will be some big difference between your distance from effective focal length to this your PP2. So that you will get that. So that's a PP2 to image distance from there you have to subtract that this 42.85. If you subtract it, you will get that one.
Sir, for but in the question there is not mentioned na, ki where is the object means where is the object distance is not mentioned na
Yeah,
question.
that's the first question I told. Your
Yeah,
PP2,
yeah, yes,
PP1, that doesn't matter. I just put a 100 only. If you put
yes,
like a, because that distance is always getting subtracted. Na?
yes, sir.
If you if you put your, you see this distance will be always constant. This distance will be always constant.
Yes, sir.
If you change your object distance somewhere here, sometimes your image will come somewhere here, such that this will change. But this will be always constant. If you put your object somewhere near, this image may go somewhere here. Still, image distance and this will go vary, but this distance will be
Mm.
always same. That is actually the property of this system, and that
Oh,
is not at all depends on your things.
okay, sir.
So yeah,
Sir, or can we say that from the equation d dash is equal d prime is equals 1 minus a by capital C? So d prime is nothing but the distance from v dash to p v prime to p prime.
means I didn't get one means.
Sir, from the last two equation, mm, like d prime is equals to 1 minus a by c. Sir,
Yeah,
this
yeah. D is equal to
d prime, sir.
D prime is equal to 1 minus A by
A upon
C.
capital C.
Yeah,
So can we say that d prime is nothing but v distance between v prime and p prime?
means this
Means the principal point to the surface point v prime in the figure of the question.
now from where from here how you are going to define that. Here actually there is no information regarding that one. Na?
No, no. So after solving the equations, means matrix.
Yeah, yeah, yeah. After solving the matrix, actually you will get to that one only. Yeah.
Yes,
After
sir. That
yeah,
distance.
yeah. If you solve this question, actually you are going to get this distance.
Yes, sir.
Yeah, you will going to get this distance only. Now you see that distance. That what are the parameter is here? One is
Mhm.
there, A is there, C is there. One is a constant. A and C
Yes,
are
sir.
actually the properties of this particular system only, and that doesn't depends anything depends on this object distance as well as the image distance. Only this A and C is a properties of this particular matrix.
System or matrix.
Yeah, so you will get like that.
Okay, sir. Thank you, sir.
Yeah,
Otherwise, we will. If the question come in the exam, we will.
yeah,
We did
yeah.
only from the Oslo.
Yeah,
So
yeah.
we
That's it. Yeah,
will
that I
how to
was saying.
calculate
Yeah,
this.
yeah. This will be cumbersome, but yeah, if some I don't know, but yeah, if they want to give some big question, yeah, they can give like this. This is then just to show this question, but yeah, you may feel that it's a simple question, but yeah, you have to
Yes, sir.
solve all the things and
Yes.
and find out solve this equation and get that values.
So sir, from this question, we did the idea the student know the about the how to matrix from first
Ah,
surface and
yeah,
then
yeah,
plane
yeah,
the
yeah, yeah,
distance.
yeah, yeah.
If the student did will do these matrices, then the student will able to solve. Otherwise,
Yes.
if fundamental is not clear, then
Yeah,
unable to solve.
nothing can be done. Yeah, that's a problem. If
Yes,
it
sir.
then no, you cannot even move any bit in that question. That's a big problem.
Yes, sir. Sir, Oslo questions will be coming in exam or software will be coming.
I don't think Oslo question they will give. Most probably they
Okay.
will not give Oslo questions.
It is for the practice and the
And
assignment.
assignments. Yeah,
Yes,
yes,
sir.
yes. Because yeah, when we are doing actually we had a project thing. I don't think you people have project. They will give a some novel idea, and based on that one you have to solve with Oslo, and you have to give the
Okay.
you have to give some presentation regarding the project how people are solving like there will be like a real camera lenses. This real camera
Okay.
lens contains some 3 4 lens in a simplest thing, but original big zoom camera will contain like a, so depends on that capacity, it will contain some 10 20 lenses inside. So but we have to make some 3 or 4 lenses
Okay. Okay.
system such that it will be a real zoom system, and how you will zoom it, that kind of project
Hmm.
used to get it. But yeah, I think you people does not have that project one. So
Okay.
for exam I don't think you will get it Oslo question.
Okay. Okay.
But yeah, so you just think that okay, this can be done without Oslo also, but yeah,
Yes, sir.
then it will be some lengthy question, so you should practice that also.
Yes, sir. Yes, sir. Thank you, sir.
Okay. So if any doubt there, then you can ask. Otherwise, you can.
No, sir. It is clear.
Okay.
Thank you, sir.
Okay. Thank
Bye, sir.
you. Okay.